let's see here. Okay, so I hope you can hear me well, all of you. Thank you for being here. I'm sorry that I could not join you guys. I missed a lot of things, fun parts as well, I heard. So, I hope that at least I can participate remotely. And so the topic of my presentation is really more to get you into not pre-preg so much, but liquid composite molding, and really with a bit of focus on what's happening at the flow front, which is something that we normally don't talk so much about. So I thought it might be useful. So what are composite processing techniques? Well, typically you know a lot about pre-preg production because you've heard just Alexios presenting, and pre-preg production really goes more into this idea of consolidation, where you have pre-mixed already in some pre-impregnation phase the fibers and the matrix, and then during fabrication of the composite, what you do is just you press, you consolidate, you remove porosity, and you get the final part. There are some other processes which are more infiltration processes, which is the other possibility, where you have the reinforcement preform that is dry. The fluid matrix you push under pressure or not, and then you get the composite at the end. So liquid composite molding really fits into the second category. And let's see, I have a video which works on me like this. I need to, let's see, get it running. So you see a flow front progressing here into a glass non-cream fabric. But you find them in many cases, and every time it's just a liquid matrix that flows into a dry porous medium. And it can also be, if you think about the impregnation that you have while you're making pre-pregs, it's also a liquid composite molding if you want, but at a small scale. But it's also true in ceramic or metal matrix infiltration, in protrusion, when you do resin film stacking for thermoplastics, typically, and so on. So you find it everywhere, and they all have the same governing laws. So what's interesting with all these things is to be able to compare, at the end, if you want to make a part, this is an old example from TechAbs, you want to compare what you predict during impregnation and what you have at the end. And you see here, I stopped it, you predict something that looks fairly uniform, but in fact, when you do a real scale experiment and you stop it, you see that, well, more or less, okay, it did what you want, but in fact, here it went much faster. In fact, here in the blue part, which is the dry fabric here, you see that it was really compressed, and that was not taken into account into the model. Clearly, we had the same volume fraction everywhere, which is wrong, so you need to change the volume fraction here, and so on. But what's interesting also to see is what's happening at the flow front. And you see when we stopped the experiment in these two cases, we see that there is some kind of unsaturated zone, which we put in yellow here, which is much bigger in one case for lactam, which was a thermoplastic precursor, than it was for epoxy. So what's happening here is really what we're interested in today. And if you look at these pictures down there, we see that we have the same fabric, same resin, but two cases here where in this case, we see that the flow front looks very uniform. And you see here, the flow front doesn't look uniform at all. And this has an influence on the quality of the material afterwards as well. So what I want to show you today is a bit, what are the conditions? What phenomena take place here? How do they influence the modeling approach? And how do we take this into account? How do they influence the measurement of permeability? And can we visualize what is happening during the flow? So what's happening physically, you all have heard, I suspect, about Young's equation. If you put a drop of a liquid, which in our case would be the polymer, the resin, on a solid, which could be the fiber, you will have the formation of a droplet, and with a contact angle. And there are some equations that allow you to find what this contact angle should be as a function of the surface tension of the solid, the surface tension of the liquid, and the surface tension at the interface, solid liquid. And basically, you have a wetting case if the contact angle is below 90 degrees. What it means is that in that case, it's more favorable for the liquid to spread on the solid than for the vapor phase to stay. In the other case, where the contact angle is too large, you have a non-wetting case, and that's what you see here, for example, on this textile, or here on this wine leaves. You have the case where it's more favorable for air solid interface to be thermodynamically than for the liquid solid interface. And you find this also, you can measure the contact angle on a epoxy droplet on carbon fiber, for example, and this is also possible. Now, of course, we don't have just one fiber, but we have a fabric when we are making composites. And so we know that there will be some capillary pressure drop taking place. It's the energy, again, that we needed to replace a solid air interface by a solid liquid interface. And so in the cylindrical tube, imagine that your composite is just a little tube, capillary tube. You all know that if you have a wetting liquid, the wetting liquid will flow up to a certain height, and that height at equilibrium will be when your capillary pressure that you have exactly compensates the density, the gravity force that you have on your column of liquid. And this capillary pressure is expressed as a function of the surface tension of the liquid, this cosinus theta, this angle that you have here, and r, which is the radius of the tube. So the thinner the tube, when it wets, the higher the capillary pressure you get, which makes sense. You know that that's why we have a paper tissue and so on. So now if you have an assembly of tubes or a porous medium, there is an equivalent delta P gamma that can be found, again with the gamma LV, the cosinus theta, and this time it's SF, which is the interface area per volume of resin. So it's equivalent to a 1 over R, if you want, in terms of dimension. So it's a quantity of available interface per volume of resin. So as you see in polymers, first of all, so if cos theta is positive, delta P gamma is negative, and it's a wetting case in that case. And then the more surface interface area you will have, the more capillary pressure you should get if it wets, which is interesting. But it also depends very much on this gamma LV, and it's a surface tension. So for polymers, if you want to look at the surface tension that we have, it's typically very low compared, for example, to metals, or molten ceramics, or water, which is here, or ethanol. We're about in the range of ethanol. No? So it's rather low surface tension. So whatever you do, whatever cosinus theta is, you will have a small effect due to the surface tension. And I'm talking about alcohol, since we're virtually in Belgium, I could not help to put capillary experiments done by Professor Adok. So now, do we have spontaneous wetting in composite processing? That's a question we can ask. And this is just a small example of a flow. You see here flow progressing into two different fabrics. And it's of course, we increase the time, but you can measure, you can see the flow progressing, and this one is much slower than this one. Even though these are the same twill fabric, the same fluid, and the same experimental condition where we actually, we measured this, we just had this fabric hanging in a little pot of water, and then we measured the flow. So what is different in this case? And do we have spontaneous wetting? Of course, yes. Now, if I was in the room, I would ask you, but since I'm not really in the room and I can't see you, I will tell you what's different. We actually treated the fabric with the corona treatment. It's not coronavirus, but it's a corona, not the beer either, but this corona pen, which is a kind of atmospheric plasma, which really activates the surface and increase the wetting of the surface. And we see it on the contact angle, on the pristine fibers that we extracted from the fabric. You see they have a pretty large contact angle. On the treated one, you see it's a bit softer, so it wets better. And we see it, if you look at the height versus time, in the pristine fabric, you go like this, and in the treated fabric, you just go much higher. And if you analyze all this, you can see that you can get the pressure, apparent capillary pressure drop. And we can see that in the case of the pristine, we had a minus 0.33 kilopascal. So it wets, but it's a very small value. And in the one that was treated with corona, we have a minus 1.12 kilopascal. So it's a four-fold increment, but it stays, of course, very small. So are these values we can use? So we have measured this capillary pressure drop. Can we use this value? Of course, the answer is no, otherwise I would not be here. And in fact, the problem is this value that you measure, it's with a given velocity, and the velocity was actually quite, I mean, you can calculate it, but you have the height versus time, and it was reasonably low. When you do liquid composite molding, most of the time you have a pressure. So it's not just a capillary rise that you measure, but it's a capillary rise with a given pressure that you have here below that forcing the fluid. And what we know from a long time ago with the experiments in tubes is that the capillary effects, well, the contact angle is a function of the velocity. So in fact, what was found is this contact angle varies with to the power third with the capillary number. Well, the capillary number is the ratio, it's a dimensionless number of the viscosity of the liquid, the velocity of the liquid over the surface tension of the liquid. So if you increase the capillary number, which means for the same liquid, you increase the velocity, then you see that the contact angle dynamic varied from a static value up to something that can really be super high if you go super fast. So in our case, because the viscosity is generally quite high, we need to worry because this capillary number can be quite high. So it might be necessary to characterize flow in dynamic conditions to estimate the capillary pressure drop value in realistic cases. So for doing this, you need to know a bit more what's happening during flow. So you need to model what's happening during flow, and you can do it using representative volume elements and doing typical fluid mechanics calculations. You have the volume fraction of liquid, pores, fibers, and then you have the saturation, which is the volume fraction of liquid over the available space. So saturation is equal to 0 when the fabric is dry. Saturation is equal to 1 when the fabric is fully filled with liquid. And so I will run you through some equations, but I will make it simple. So we assume that we have a unidirectional flow, saturated, isothermal, in a non-compressible fluid, in a rigid porous medium. So everything is basically static except just the fluid moving. In that case, the mass conservation equation is written as you would do in a normal pipe flow by the divergence of the velocity. The superficial velocity is equal to 0. And then you have the famous Darcy's law, which is a momentum conservation equation, which tells you that the superficial velocity, which is the flow rate divided by the area of fabric that you go through, is in fact it's 1 minus VF, where VF is the volume fraction of fibers times the flow front movement, dL over dt. And it's equal to minus K, where K is the permeability of the porous medium, eta is the viscosity of the fluid, and dP over dx is the pressure gradient. Now, if you are in a non-compressible fluid and everything, since the divergence of velocity is equal to 0, you can just do d over dx of this part, and that will tell you that in fact d, the second derivative of the pressure versus x is equal to 0, which means dp over dx is a constant. So we have a constant pressure gradient. And so we can write it here. We have a constant pressure gradient. We can solve the equations. We can replace this dP over dx by delta P over L. And then we just need to solve this very simple equation. And we find that L, the flow front position, moves with the square root of time, or L squared moves with time. And this coefficient is proportional to permeability, to delta P, and inversely proportional to viscosity and 1 minus VF. Now, what is this delta P? And that is the main question, because most people say, well, delta P is what? It's the pressure that I have here minus the pressure that I have applied here. And if you have 0 capillary pressure, maybe, but if you don't, you need to take into account that, in fact, here, the pressure may not be exactly the atmospheric pressure, but you may have a pressure which is equivalent to this capillary pressure drop. So there is one big assumption that is made when we solve the equation, is to say, it's called the slug flow, because that's what is said in soil science, that the capillary effects act exactly at the saturated flow front just here. And then this delta P is in fact the delta P applied plus the delta P gamma. So that's the delta P total, and my delta P applied is the pressure that I have here minus the pressure here plus this delta P gamma. So if delta P gamma is negative, in fact, my little the pressure will be below. So I have like a negative pressure that sucks, if you want, the fluid in there. And if my delta P gamma is positive, then it means that it does not wet, and I have to overcome this capillary pressure to force the fluid to penetrate into the porous medium. So in all rigor, this delta P gamma is not a constant. It varies because cosinus theta is a function of the, as you know, of the fluid front velocity. So, and it's also a function of actually the viscosity. So we assume the viscosity remains constant here, but that can also change. And we need to define it experimentally, maybe in a flow experiment, instead of trying to find a cosinus theta. And so that's what we did a long time ago. With a constant flow rate experiment, if you do a constant flow rate, solving the same equations that I showed before is very simple because Q is a constant. You impose a flow rate. So dL over dt is a constant. So the flow front moves linearly with time. And then you can, if you measure, so what changes, of course, because this is constant. So as L increases, P increases. So you have a pressure at the entrance that will increase linearly with time. And if you measure this pressure, you will see a linear increase with time, which gives you actually the permeability as well, if you know everything else. And there will be a plus delta P gamma, which will tell you what is the value of delta P gamma. So if you do different experiments with different flow rates and so on, you should be able to find what is delta P gamma with the flow rate. And we did this different tests, and you see that it kind of works. You have a constant increase of the pressure, and then the constant increase of the pressure, of course, starts from zero because we are, doing a real experiment. But if you take the slope and you extrapolate, the slope extrapolates to a certain value, which would be your delta P gamma measured for this value of capillary pressure drop. And then you have this, knowing Tanner's law, if you increase the capillary number, your delta P gamma should increase following this equation. And it kind of works. You see that the capillary pressure drop we measured, in our case, we had a quite high capillary number. It was with the epoxy resins into NCF, but we see that it increases as I increase the velocity of the resin. I have this capillary pressure drop, which remains quite small, which has an influence, but it remains, it increases with the capillary number, sorry. And then we extrapolated that this is the static contact angle that we measured. So if you just look at the static contact angle, your values are completely wrong because you think it will wet, but in fact, it's actually non-wetting, and you have a positive capillary pressure. So now, how does this influence the measurement of permeability? That's the next question you can ask, because you can say, well, who cares, because this is a small value. It's like a few kilopascal. If I apply a pressure of, a few bars, I would be much higher. So, and that's what most people have done. They've just said, who cares? Now, if you don't care, it's fine. You will get values that may be a bit wrong. And in permeability, measurement of permeability, this is something that people have been discussing a lot. And I stole those from my colleague Joël Brea because I was too lazy to take hours. But you see, you measure the flow front progression. What you do is that you use a fluid with a well-known viscosity, like silicone oil or whatever. You apply a constant pressure, and then you plot what is the flow front position versus time, and then you can find the permeability, which would be linked to this psi square, which is the slope of L square over time, which should be linear, and then you divide by delta P. Now, of course, you don't know what delta P is, so you say, well, delta P is the pressure that I had in the air minus the pressure that I applied. So I know delta P, and I find K, which we would normally call K unsat. Doesn't mean that the flow is not saturated, but it means that it's a measurement, it's a dynamic. I would call it K, flow front, or K dynamic. But anyway, everybody calls it K unsat. Just to tell you in any case, permeability is not easy to measure. And this is from the permeability round robins that were done over the years, in which our friends in Leuven also participated. You see that if you ask a bunch of groups to measure the permeability of a fabric, and you don't give them any guidelines, you just say, do whatever you like as you would do at home, you get this type of measurement results. So these are many different groups measuring, and you see that you have a lot of scatter, and you know, what is the permeability of that nice carbon twill? Is it 2 10 to the minus 10, or is it 12 10 to the minus 10? Now, of course, second round robin, we took the permeability, same fabric, we gave precise guidelines. So it was an unsaturated permeability measured using silicone oil with given geometry and so on. And here you see, okay, a bunch of guys did not follow the recommendations. So they are, but the guys who followed the recommendation, we were much, much closer. And we have a value of permeability here that is quite, at least everybody more or less agrees with about 21% variability, which is not negligible, but better than, you know, an order of magnitude. Now, are these values good? Are these values the real permeability of the fabric, or do we all agree on the wrong value that we have been measuring because we measured K unsat and silicone oil? That's a main question. So we can always say, well, if we at least all agree with the wrong values, we can compare each other and compare our methods. And you know, if I increase the permeability of a fabric, I can measure it. But if we want to really know what we're measuring, we may need to ask ourselves a bit more questions. And one thing we can do, when you measure this unsaturated permeability with the flow front, you can also, at the end, let the fluid flow through the outlet and measure the saturated permeability with the flow rate. So you know what is the flow rate that comes out, you measure it here, and you know, you divide this by, you know the full length of the fluid, the area of the textile, and delta P. And this time, because you don't have any capillary effects, because everything is fully saturated, delta P is the real delta P. So it's really the pressure here minus the pressure at the inlet. Whereas here, when you measure it, the delta P is wrong because you also say it's pressure here minus pressure at the inlet, but you forget about the capillary pressure drop. So what we observe is that K sat and K unsat most often are not equal, but they should be equal because, you know, you measure the permeability of a fabric, and the permeability of a fabric depends only on the fabric. It's a geometrical feature that depends on the volume fraction that you have and on the arrangement of the fibers. It should not depend on the way you measure it. And so what can we do with this? Well, we know that in this measurement here, delta P is wrong. So the K unsat is a K unsat that is measured with the wrong delta P. So if we do a bit of calculations here, you know that the real delta P total is the one that takes into account delta P gamma, the capillary pressure drop. So if we know that the slope that we measured for L square versus T, when we find the K unsat, we use only the delta P, just the normal delta P. When we do the K sat, if we could do it, it needs to take into account the delta P gamma. So if we divide this one by this one, we have a ratio of K unsat over K sat that a lot of people have talked about. Joël also from a long time ago has started to talk about this. And people have been measuring this K unsat over K sat, and they see that it's not equal to 1, but it should be equal to 1 only if delta P gamma is completely negligible compared to the delta P the applied pressure that you put in your measurement. So, and we say that this ratio, if it's below 1, you have a non-weighting case, and if it's above 1, you have a weighting case. So in this case, RS is a good measure of the capillary pressure drop, at least we hope so. And this K unsat is a priori not a good measure of the permeability because it will depend on the fluid and the test condition and the ratio of this delta P gamma over delta P I. See, if we go back to the glass fabrics that we treated with the corona treatment that I presented before, we did measurements of permeability on the pristine and treated fabrics. And you see that, okay, the permeability, it was a saturated permeability. and unsaturated. We did both. So we see that saturated and unsaturated permeability are not fully equal. They are kind of not that far away. And especially if we increase the VF, we are quite close. We see that, okay, permeability decreases with volume fraction as expected. And now if we do this ratio, RS, we see that this ratio for the pristine fabrics is below 1, which it doesn't wet. And for treated fabric, it's above 1, which means that it wets. So at least it's coherent with what we did, because we treated with Corona and we know it increases the treatment while everything else remains the same. And if we calculate the capillary pressure, we extrapolated from this RS value, we see that the capillary pressure is positive. Here it's inverted to be, otherwise it doesn't work. So here it becomes positive, and we see that indeed, and then here it's negative. And interestingly also, we see that as compared to what we had just with the capillary pressure, just the simple, capillary rising experiment, we had very low values. Here we can get to values that are a bit higher, also 3, 4. So it works. We can also use this, and that was recently done by Hirun in the paper we just published, which on using this time fibers that are grafted with carbon nanotubes. So these are this kind of all these fibers are grafted with a forest of nanotubes, of carbon nanotubes. We managed to measure the permeability of these guys. And of course, the permeability as compared to the pristine alumina, we did saturated and unsaturated. We see that when you have these grafted guys, permeability remains quite low because they are there. But interestingly, we found that this ratio for the alumina fabric was in the range of 0.8, 0.9. So we were, for the alumina fabric, in a range that, this permeability ratio is such that it doesn't really wet. But when we had the grafted fabrics, even though permeability was quite low, the unsaturated permeability was very high compared to the saturated, because we went up to 2.9, so a super high ratio. And we used it as a proof somehow that the CNT strongly enhanced the capillary effects. So at least with the fluids that we used, and then we have, we help impregnation thanks to the CNT that actually suck up like a little sponge the fluid that goes through. We can also use this technique to compare different fabrics. And this was another example that we did where we compare two fabrics. One is the G-weave, it's a normal woven plain weave glass fabric. And this one was a fabric made by Shomara, which is a non-cream fabric made for having a super high permeability. So what it had is, you can barely see, but it has a lot of stitch, like every 3 millimeters here, you had like some kind of, a toe. And then you had the bottom, which was the UD toe. So it's a kind of a long UD, but with a lot of cross toes that are quite thick here. So that makes really big channels in between. We can actually take a look at it here with the CT, and you see that the G-weave, when you compact it, you start to have a very compact, porous medium with a little bit of pores. And in the G-ply, because of these big toes, when you compact it, you still have really, really big interstices. And if you do a permeability measurement, you see that the G-ply, as expected, has a high permeability, whereas the G-weave, the normal one, has a normal permeability. So this is good for, this was done for polyamide, which have a reasonably high viscosity, so you can really increase almost by an order of magnitude the permeability, so you can really go in much easier. We try to do unsaturated permeability measurement with these same fabrics. And then for that, we varied a lot the capillary number just to see what we measure. And to vary the capillary number, we also varied, of course, the velocity, but it's a bit tricky to vary to a certain extent. So we also varied the eta and gamma. So we used water, PEG, polyethylene glycol solutions, and then silicone oils, so that we get a range of viscosities, and of course, a range of surface tension that we need to take into account. And then we did another problem is that if you have a constant pressure experiment, the capillary number actually changes with time because the velocity is not constant. So we found a range of analysis where the capillary number remains more or less constant after the beginning of impregnation in this range. And then we found, interestingly, that if you do a wide range of capillary numbers, the RS ratio in this case was very high at low capillary numbers. So the capillary effects dominates. That's what we expected. And we have a really high, we can go to, if we go very, very slowly, everything is just sucked up in the toes. And in particular, also for the G ply and the G weave, which is easier because it's a more narrow fabric. And then if we go above a certain value, we tried everything and we wanted it to go down. But in fact, what we see, because the hydrodynamic effect dominates, and in particular for the G ply, the effect, these big channels are really dominating the flow. Whatever we do, if we go super fast, we measure the same permeability because it's the permeability of the big spaces that is giving the value of permeability. And if you look at the flow front, you see if you go slowly, you have a normal kind of more or less equilibrated flow front. If you go super fast, you have a very large unsaturated flow. You see here, those bundles, they are just not at all impregnated. So they are completely dry along a super long region, whereas the flow, the liquid has gone into the channels. So can we trust this data? And what is the effect of this large unsaturated zone on the composite performance? So that's the next question I will answer if you're still alive. So is the slug flow assumptions correct? Well, slug flow assumption, as I mentioned, it takes the, well, it says that basically the flow front progresses in a very, very flat manner. And here I have purely dry fabric, and here I have purely saturated fabric. So the saturation, it should go from 0 to 1 drastically. Here, you know, of course, by looking at it, that saturation is 0 here, it's 1 here, and here I have a very slow progressive saturation, maybe, or maybe not, well, whatever. So it's linked to the bimodal pore size distribution, and any fabric has it. And you see that you have, you know, a lot of dark areas, which are big pores. And then, oops, sorry. And then you have micropores in between the fibers with super high volume fraction regions. So when you're impregnating, of course, the flow will want to go, depending on many things, either rather here in the big spaces or rather here in the micropores between the fibers. And this has been seen now by many people. I didn't have time to put all the references, but you can find them or ask me. It's the result of the dual scale nature of the fabrics. And what we observe is that if the capillary number is low, we have basically we don't push very much and the velocity is very low, then capillary effects are really dominating. So what you have is that the flow goes inside the fibers, the toes, and is lagging behind in between. If the capillary number, so the velocity is very high, you will have the contrary. So I push a lot, it goes in between, and the toes are lagging behind. And the interesting, very interesting result that was found is that if you look at the void contents in the final part that you cure, you demold, if you go super low with the, you know, you let the capillary forces do their job, you will entrap a lot of porosity. Whoops, sorry. You will entrap a lot of porosity here in between the things. Whereas if you go super fast, you will not entrap porosity in between the toes, but you will entrap porosity in the bundles. And so it was found that the void content actually around a certain capillary number, which is the optimal one, will increase a lot if I go too slow, and will increase a bit less because of course it's in the toes, so it's a bit less if I go too fast. So if I want to go really fast when I do impregnation, especially for RTM and so on, then I may end up actually shooting myself in the foot, that I create a lot of porosity, whereas I have to go at some, you know, nice optimal condition. And there are lots of works on how to find the optimal conditions using finite element models. I mean, if you know what is the optimal capillary number, you can actually adjust the pressure ramps in your part, and they've done a lot in Montreal, and it actually works really well, and you can optimize at least the quality of your part while keeping time for impregnation that is decent, of course. So now, of course, it's interesting to see what's happening, because in what was observed a lot is in the final part. Now, if I want to see if I stop here, I cannot stop it. But here I have a capillary driven flow, and you see that it's really, driven here. And here I have a viscous driven flow, and you see that it lags behind, and these guys will finally and you see a lot of pores also taking place everywhere that are being filled up and so on. So can I get snapshots of this? And can I get measurement of the saturation is the next question we can ask, because it's nice to see this, but of course I can stop these pictures, but it's a bit tricky to really see what's happening. So one thing that we did is to get snapshots by using a resin that would reticulate with UV. So in this case, if I just put back the arrow and I put this, you say, okay, I let the resin flow, and then at a given time, I illuminate with the UV, and the resin is stops flowing because it's cured. Of course, it works only for very thin resins and so on, and we're working on improving this idea. But we can stop, and we can observe then a posteriori what the flow front looks like. And that's where you found those nice pictures that I showed you recently. So, and if I do this, then I can look at the results, and I can compare again this pristine and this treated fabric that I use as a fil rouge for this presentation. And you see that, okay, at a capillary number equal to 0.0014, so quite slow, and a filling time of 6 minutes to get to this position, I have something that looks a very uniform flow front. And that was for the treated fabric. Now, if I look at the pristine fabric, I'm not at the uniform flow front here, but I'm more at I see that there is some lag behind. So then if I look at the other guys, clearly here I'm going very slowly, and I'm in this case where I have some porosity clearly present in between the toes of the fabric, and some kind of unsaturated zone that I can measure here. And then if I go too fast, I see that I'm just leading flow in between with these guys here that are still dry. And then I can also measure the length of this unsaturated zone and look at the different things. Of course, here the time for fill is 1 versus 20 minutes. So you see a bit, why sometimes we are ready to accept these things. Now, this was for transparent. If you have non-transparent, like carbon, which everybody talks about and is more maybe interesting, it's a bit tricky. And there have been a lot of attempts, maybe using visible light transmission with some kind of, this kind of fluorescent things. It's a bit difficult because you cannot really find the microvoids, but it gives interesting results. You can do it by X-ray tomography, of course. But the problem with X-ray tomography is this was done with a synchrotron source. It's worked by guys our colleagues in Madrid, but they took 120 minutes per scan. So if you go really fast, of course, the flow front has gone way, way beyond. So you have to make a kind of a weird impregnation. And they did recently a new paper where they improved this a bit, but still it's a bit limited. And then some other people tried with magnetic resonance imaging, and there they had a scan time of 21 minutes, but they also got some interesting results. Our work in progress is to continue to look at this snapshot. So we can do it by doing thick cross-section, non-translucent fabrics using frontal polymerization, and it's in progress. And here it's looked at the beginning, it was really burning. Now it's not burning so much anymore, we've improved. And then the other way is to do a flow visualization with X-ray phase contrast imaging. So this looks big, but it's it's an X-ray detector in the back and some gratings. And I will show you a bit more about those guys. Next slide. Yes. So this is a comparison of cases which I just got from Elena. So this is a capillary driven flow where you see this is the balance flow, and this is the viscous dominated flow. And in these cases, well, you need to do a lot of image analysis, and we're working on improving this. But you can see the difference in the flow front, depending on the different cases. And this is in a thick carbon fabric. Actually, the thicker it is, the better for this phase contrast. So it's good. And then you can measure saturation versus position and time. And then you can really extrapolate the saturation curves for different cases. And just after the flow ceases, you can also see, and this is with a contrasting agent to improve the contrast here, but you see in the capillary dominated flow, after we stop the flow, you see a lot, I have to put my laser pointer again, a lot of voids remain. So we can also use this tool to measure how the voids concentration evolves with time after we finish the flow. The balanced flow, we see that it's actually very good with a little porosity. And in the viscous dominated flow, well, it's a bit difficult to see porosity because it's within the toes, but hopefully we can see some differences. So how to model all this? That would be my last little slide, and before we finish, so that you guys can have lunch as well. So we can use a multi-scale approach, which is normally what people have done, and there are, again, many references on this topic, is to say, well, I have fibers here, I have a gap here, and I can model the flow. In this case, for example, the flow is going faster in the gap and slower in the toes. And I have some transverse flow that's going here. And I do a coupling at the interface between the Darcy's law in the toe and the Stokes flow in the region in between the toes. But this needs to, of course, know well the microstructure, which now with CT scans you can, but the capillary effects in the toe, because then how does it impregnate here? And what again, the delta P gamma that you have everywhere is a bit of a catch-22. So it can be done, but it's again, is a bit tricky. The other approach, which is one that we have followed in the past and are still following, is to use a fully unsaturated multi-phase flow approach. So where you look at fluid flow, not only you don't assume that everything is fully filled, but you have porosity here. So you have a volume fraction of pores that is also present. So the volume fraction of liquid is also something that you need to know. And you also have possibly, in that case, velocity of the solid, we can say it's 0. But we need to know the saturation, so the ratio between the liquid and the solid phase. And we measured saturation curve, which we extrapolated from these flow measurements. And we saw that depending on the capillary number, the saturation curve is actually different, which means that the capillary effects are different depending on the velocity as we suspected. So I will stop here because otherwise I can go on for hours on these topics. But the idea was to show you that, okay, in liquid composite molding processes, but whether it's normal LCM or RTM, even if you do pre-pregs or whatever, you have impregnation and capillary effects will take place close to the flow front, and they will affect the flow kinetics and they will affect the part quality. If you do unsaturated permeability measurements in your work, you should be aware that these can depend on the flow kinetics and model fluid choice. And if you want to enhance the permeability by having big channels, you also exacerbate the dual scale nature of flow. So, but the K unsaturated that you measure is correct, because since the large channels dominate above a certain speed, finally, you don't really care. Unsaturated and saturated permeability measurements can provide indications on the nature and the magnitude of these capillary effects. So it's not we're not completely helpless. There are ways to measure these effects. And you either by doing, pressure measurements like I showed, or by doing flow front observation, or by doing both, which is also possible. And then the optimal capillary number is linked to the dual scale dimensions of the textile and to the fluid interface properties. So what is this optimal capillary number is something that everybody measured. We know for a normal fabric, it's close to 0.01 or something like that. And it's to be further elucidated really to find how this capillary number evolves with the textile dimensions and the interface properties. And with this, I will stop. I'm ready for questions. I want to thank all the others, including Barish, Elena, and Hyun, who gave me a lot of material for this presentation, support from SNF and EU. And before questions, I have to tell you that next year, if you don't know, ECCM 20 is in Lausanne. So reserve your calendars, 26th to 30th of June, 2022. And we hope that we can see you all in beautiful Lausanne very soon. So now I'm ready for some questions if you want to ask questions.
Thanks very much.